My name is Dávid Ferenc Vránics and I'm a PhD student at the Hungarian National University of Public Service, specialized in the security of unmanned aircraft systems. In the meantime, I've been working at Ericsson Hungary as a developer of testing solutions and cloud systems. I am an ISTQB advanced level test analyst and security specialist, and I am an overall aviation enthusiast. Hello and welcome everybody to my presentation at the 10th Hungarian Software Testing Forum. I'm really excited to be here to share my testing experience about my cloud-controlled drone system. The system looks like the following. My hand-built DJI F450 drone carries an Android smartphone which is connected to the ArduPilot Mega autopilot board via USB. An app called MAV Downlink relays the MAV-link messages between the cloud system and the drone via 4G. The cloud system serves the drone control service, written in Python, a central MySQL database, and the web GUI service, which is HTML, PHP, JavaScript based. Smart devices or computers can then connect to the web page, and then the user can issue commands to the drones, while the map displays the logged-in drones' positions using the Mapbox framework. At the field, a generic laptop with a 4G dongle was used for this purpose, plus the typical 2.4 GHz remote controller was utilized for manual flight and emergency control. The service was hosted on a small virtual server based in Chicago, Illinois, US. This means a 15,000 km communication round trip. Still, the measured latency was only 150 milliseconds. This proved more than enough, as the GPS sampling rate, the drone heartbeat, and the map refresh rate were all set to be 1 Hz. On this slide, you can see the details of the airspace and some legal info about the first manual flight. Because of my affiliation with the Hungarian National University of Public Service, I was fortunate enough to test my system at the MH86 Szolnok helicopter base, while my other colleagues held a testing and practice session. As required by law, the temporary airspace was activated and deactivated by my air traffic controller colleague, Major Csaba Fekete, who is the legal owner of this temporary airspace. He was also in constant radio contact with the tower and the other aircrafts. The first flight day was a busy day at the Szolnok helicopter base, as an international military exercise was under preparation. I still got my flight window approved, while there were United States Apache and Chinook helicopters, and Hungarian Hind, Zlin, and AN-26 aircraft operating at the airport, departing and arriving or practicing touch and goes. Plus my colleagues were also conducting tests with a meteorological balloon. Basically, I just got my own little air show for the day. The pilots were also completely cool with us. The tower asked an incoming Hind pilot if we should land our drones. He said, "No, let the guys do their job." So we started testing. First, I asked Csaba, who is also a certified drone pilot, to take my drone on its maiden flight. During this, I was observing the telemetry data and the map display of the cloud service. Everything seemed fine. Next, I took over the controller, took off, hovered a little, then attempted landing. But as soon as the drone touched the ground, it tipped over in the grass and the USB cable disconnected. The server logs showed that the connection loss and later reconnection caused no server-side disturbances. The last known location of the drone was logged, and the service recovered when the drone went back online. I count this as a success. Almost half a year later, I was prepared for the autonomous flight tests. Same airport, same procedure as before, but slightly different temporary airspace. This time, my colleagues were conducting practice flights with the drones, including a DJI Inspire, DJI Phantom 2, and the BXAP-15 fixed-wing UAV. We applied horizontal separation to avoid collisions, plus I set up geofencing and emergency manual control on my custom drone. Some test cases were performed on the ground, arming and disarming the rotors, automatic takeoff and landing, mission upload, deletion, and override on the autopilot. Arming and disarming worked, takeoff and landing did not. As later I found out, because the old firmware and hardware of the autopilot did not support it yet. I also realized that the coordinate systems of the autopilot and the Mapbox display framework were not compatible. I'll show you later why in this presentation. After a quick fix in the code, came the moment of truth, the autonomous flight. As the takeoff and landing commands were not supported by the autopilot, I took off manually, hovered about 5 meters above the ground, then switched to the autonomous mode. The drone indeed came to life and approached the assigned waypoint. It then started to hover, shook by the wind. If you've been to an airport, you may have noticed it's almost always windy out there. So after I took back the manual control over the drone to attempt landing, a sudden gust of wind just flipped it in the air, disconnected the battery, and the drone just fell helplessly to the ground. All the props were destroyed, the GPS mast, and even the frame was broken. But it was a success. The system worked, the commands worked, the drone flew on its own, so I happily packed up the remnants of the drone and headed home. Home, where I later built the infrastructure for other tests. On the laptop, in the middle, I set up an OpenStack cloud system with DevStack, and it acted as both as a controller and compute node. The laptop on the right may be familiar to you. I used that one previously during the flight tests in the field. Now it acts as a second compute node. OpenStack heat templates were used to orchestrate autoscaling, load balancing, and periodic health check of the service. Finally, on the left sits a laptop which is running my proprietary Mavlink protocol simulator, which is based on the Titan TTCN3 compiler and executor framework. This software was used to simulate 100 parallel UAVs in the cloud system to generate load to verify different aspects of the cloud. The autopilot of the actual drone was used as a test oracle, then the messages were fed into the code. The machines were connected using a generic home router and Ethernet cables. Horizontal scaling refers to creating more or less parallel virtual machines when needed, for example, based on processor load or network throughput, as opposed to growing or shrinking a single virtual machine when the resource needs dictate so. The latter is called vertical scaling. When creating an OpenStack heat scaling policy, an internal URL is generated. This URL can be used to trigger the policy manually to perform the configured adjustment of resources, for example, to scale up or down an auto-scaling group. During manual scaling tests, the above-mentioned method was tested to trigger a scale-up. It worked, a new machine was created and came online. Scaling can also be bound to a resource alarm, for example, to CPU load. So when the CPU load reaches a threshold on a virtual machine, the event can be used to start another parallel VM or to delete it when the load is low enough to be handled by fewer machines. This was tested by simulating 100 drones in the system, but additional load was needed to reach the threshold. So I logged in and started an infinite loop. After the next polling period, the alarm was triggered and the cloud scaled up with 1 VM. Next, anti-affinity. It is desirable in some cases for the VMs to not cluster together. For example, to ensure that if a server gets destroyed or otherwise becomes unavailable, the other servers in other locations can take over. Otherwise, affinity itself could ensure small latency between the VMs, but it is not required in our case, as there is no communication between them. While testing static placement, 2 virtual machines were created immediately. One got created on the first compute, the other on the second compute. Pass. To test dynamic placement, a single VM was created, then a scale-up was triggered. The second VM was created on the other compute. Also pass. To test robustness, the service was originally spread onto 2 compute hosts. While simulated UAVs were generating active load on the virtual machine on the second physical host, the network cable between this host and the network router was disconnected, thus simulating the loss of the machine. The health monitor component noticed this by doing periodical TCP-based checks on the service, and the virtual machine status was flagged error in the list of servers. The load balancer then rerouted the incoming connections towards the other available VM. This way the service survived and suffered no noticeable interrupt. In the end, the network cable was reconnected and newer clients were routed towards the second host. Robustness tests passed. For ease of connection handling, single UAVs are preferred to be routed to the same virtual machine by the load balancer every time they connect. This way, some control communication, for example session build-up and teardown, can be spared for individual messages, the network cost of which is comparable to the actual UAV data in case of Mavlink protocol version 1. During client reconnection, a client logs in, logs out, then back again just to test if the resources are cleaned up properly on the server side and new resources are properly created. This property is a hard precondition of the previous test cases, like service restoration. Furthermore, the client's messages properly went to the current server, not getting routed to the other VM. The same could be observed when the network cable was disconnected, the client was properly migrated to the other server, then after the network cable was reconnected, it stayed and messages still got routed to the current server, not the old one. These tests also passed. So, my findings and recommendations. As I mentioned earlier, I noticed that the coordinate systems of the autopilot and the Mobbox framework are not compatible. This time the longitude and latitude were switched, causing a Hungarian coordinate to translate into a place somewhere in Saudi Arabia. The consequences of this error in a flight system could be fatal, with a possible total loss of control. There can also be other deviances in the coordinate systems, for example, decimal versus degrees notation, north, south, east, west versus negatives and positives. So, double check your position format standards, time formats, and generally the compatibility of APIs during system integration. 4G worked for me surprisingly well, with around 150 milliseconds of latency between the drone and the Chicago server. This value is negligible compared to the 1 second refresh rate of the map and the 1 Hz data position sampling of the drone. This could of course be configured to be more frequent, but my experience is that 1 second is practically enough for position, sensor data or heartbeat messages when a drone is in autonomous mode. Of course, manual control and video stream would require more bandwidth and quicker response times. This is where 5G would come into the picture. Fortunately, my testbed does not rely on specifics of the communication channel, so it could be seamlessly upgraded just by fixing a 5G capable smartphone instead on board in the future. Destroying your hardware is not a bad thing. It comes with a lot of extreme data, one less unexpected to be expected. You just have to make sure you observe it close enough. Also, always prepare with some spare parts, extra batteries, etc. for your hardware of choice. All the technologies I used while building this system are open source or free to use. Back in 2014, when I started prototyping this system, civilian drones were not as sophisticated as today, and some people I know didn't believe a cloud-based unmanned aircraft system could be worth or even possible implementing. Nowadays, there are closed source systems around the world that serve this purpose, but I hope My story inspires other initiatives to build a secure but open system and to properly test them. Always double-check hardware, firmware and protocol specifications before system integration. Old hardware with new firmware can be just as problematic as new hardware with old firmware. Not even mentioning protocol versions here. In my case, the drone simply didn't take off on its own, but imagine if the emergency procedures are not triggered properly or manual control cannot be taken. So backup or emergency control methods and geofencing are must-have for autonomous drones, in my opinion. Of course, these side channels must be also completely secured. During flight tests, a separate pilot and observer role is highly advised. While you are flying manually, you can't look at the data in real time. And when you are looking at the data, you can't watch out for the drone. Remember, safety first, plus please fly legally, even though it is cumbersome currently in Hungary. My overall feeling is that, as I've shown, a cloud architecture can enhance the safety regarding unmanned aerial vehicles and could possibly host more features such as automatic collision detection and avoidance. And with that, I thank you for the attention, and let me also thank Major Csaba Fekete for flying with me and my thesis advisor, Colonel Mátyás Palik, PhD, for the constant support. Most of the pictures in this presentation are my own photos or graphics, otherwise the source is added as alternative text. Fly safe!